Okay, welcome everyone to the Martian Meteorites session. I'm one of the co-chairs, Chris Hurd from the University of Alberta. Introduce yourself, Adrian.
Hi everyone, Adrian Bros, Purdue.
And I'm Sierra Ramsey, a PhD candidate at the University of Nevada, Las Vegas.
So Adrian and I are your co-chairs and Sierra is the moderator. My computer just tried to go to sleep. Okay, we have a full session of 6 talks of 10 minutes each, followed by a 25-minute discussion. So reminders to speakers that you have at 8 minutes, you'll get a warning, a flashing yellow. We'll give you a visual warning as well to let you know that you have 2 minutes left to wrap up. And then you're expected to wrap up at the end of 10 minutes. And if you see one of us stand up, then that means you're done. Reminders to audience members to please keep your phones on silent. Also, no photography or video unless previously arranged with the speaker. And also, we expect to also remind people to keep it civil and adhere to rules of expected behavior. If you want to joke about Canada being the 51st state, you can talk to me in the parking lot afterwards. So think then we'll have our first speaker come up to the stage. We do need to give you wait a few seconds here, Alan, before we actually get started. That went faster than I thought it would. We do have online participants as well. We don't have any online speakers. We have online participants, so we will be monitoring the chat for that. Online participants are asked to please put their questions in the Q&A part so that we can then monitor that and bring that up later. We do encourage that discussion, that participation definitely, and we'll do our best to make sure that those questions are included in the discussion section a little bit later. Okay, I think with that, I'll turn it over to Adrian, who will introduce our first speaker.
First speaker today is going to be Alan Treeman from LPI talking to us about Nakola meteorites. Go ahead, Alan. Thanks.
Okay, thank you very much. I'm going to talk about the Nakola meteorites, one of the groups of Martian meteorites, and they are characterized by having lots and lots of olivine and augite pyroxene in them. That's how the group is defined. And so I'm going to be presenting a new view. The background for this, of course, is that the Nakolites have been interpreted forever, basically since 75 when Reed and Bunch talked about them, as being cumulates, crystal cumulates, accumulations of crystals of augite and olivine in a basaltic melt. And so that has led many of us over the years to search for what the parent magma might be, because it's only by knowing the parent magma that we can understand what's happening in the mantle, how they were formed in the mantle, what processes have happened since then on their way to eruption. What enables this talk is an absolutely fantastic data set from Udry and Day, and then continued by Ramsey on the chemistry and petrology of the Nakolites. They got big samples to analyze essentially every element in the periodic table, physical properties, mineral chemistry, phase proportions, a lot of stuff I would talk about. It's absolutely fantastic data set. And I'm going to take it and do stuff they didn't intend with it. This is not the result I was expecting. What I ended up concluding is that most Nakolites are not crystal cumulates, that they actually represent magmas or lava compositions. And this has a number of interesting implications. There's some kind of creepy component in the mantle that's affected them. And to accommodate having peroxenitic magmas, you then have to have some kind of pyroxene-rich mantle to have melted to make them, which I think is a wrinkle on Martian mantle petrology. Okay, so let's talk briefly about what a cumulate igneous rock is. You start out with a magma in gray, and I'll just give it some lanthanum and ytterbium numbers, lanthanum being very incompatible, ytterbium not so much. So if you start off with a magma like that and collect some crystals into it, crystals settle into it, the lanthanum ytterbium ratio stays the same because the augite and the olivine take basically none of either of them. So the ratio stays the same. That just reflects the magma in between the crystals. But the lanthanum content itself decreases because that's all in the mantle and all in the magma, and it gets reduced by how much of the crystals have settled into the system. So that's the basic thing I want to talk about here. I'm not going to have time to talk about the compatible elements given our short time here. Okay, so let's look at the rare earths then. On the left here is a sort of standard rare earth diagram normalized to CI chondrites like always. And this is essentially the same as in the Udry Day paper. And what you can see there is that there's a huge range, like a fourfold range in the amount of light rare earth elements, the most incompatible elements, and a much smaller range in the heavy rare earth elements like ytterbium, which is the one I'm looking at mostly. So let's quantify that here by taking the lanthanum abundance and comparing it to the lanthanum ytterbium ratio over here. And if I'd had a chance to revise this figure before it getting sent up, I would have, this symbol ought to be a black circle, one of the Udry and Ramsey ones, and one of these also. So there's a little bit of a, I wish I'd had a chance to revise it. Also, the Yamato 593, that should be red, and I'll talk about the difference between red and black in just a second. Okay, so so this is the kind of diagram that one sees for, like in this case, lanthanum versus lanthanum ytterbium. And this is not just for the rare earths. If you look at any of the other highly incompatible elements, thorium, tantalum, niobium, potassium, rubidium, even titanium and aluminum, you get a very similar kind of diagram where the bulk abundance of this highly incompatible element increases with the lanthanum ytterbium ratio. So I'm not just doing rare earths. This is basically the whole data set that we're looking at here. Okay, so first of all, what this means, this diagram, there's not an enormous surprise, is that there's a range of magmas here because the lanthanum ytterbium ratio is a characteristic of the magma. It doesn't depend how much olivine and augite have accumulated into it. So there's a range of original magma compositions here that have a range of light rare earth enrichments in them. Okay, that's cool. The second thing that's really just mind-boggling to me about this was this linear array here. And if you do a linear regression, that has an R squared of 0.95, which is pretty impressive. So what does that mean now? Well, okay, how do you get this if these rocks might be crystal cumulates? Remember that a crystal, like the lanthanum abundance of a crystal cumulate depends on two things: on the lanthanum content of the original magma and how much of that magma is left, how much, what proportion of accumulated crystals there is. So, whoops, excuse me, wrong button. So every one of these points somehow must have balanced out the original lanthanum content with the amount of cumulus material so that they all ended up falling on this line. Every single one of them. This just boggles my mind. I don't know how that's possible to do. The more reasonable interpretation, I think, is that the lanthanum content here is a characteristic of the magma, and that each of these points is a magma composition. So what we're looking at here, except for the red points, are actual magma compositions. And like I said, this holds for all of the highly incompatible elements. Now, what about these three? Remember that that's actually red. Those are what crystal cumulates should look like. For instance, if you started with, say, that point, which is the MIL 03364 Knocklite, and took a magma of that composition and added about 50% augite and olivine to it, you'd end up down at the Knockla composition. So what it looks like to me is that we have this range of magmas here, and that a couple of them are actually crystal cumulates, but most of them are not. Most of them have their lanthanum and lanthanum ytterbium ratio and lanthanum content set by the original magma. And I can tell I'm running out of time here, no matter. skip that one. So the question is, next is, are these compositions reasonable? And the answer seems to be yes. One bar liquidus compositions, are these reasonable magmas? The MELTS program gives about 1255 C, which is not an unreasonable number. Crystallization sequence looks reasonable. Viscosity is reasonable. Are they ever co-saturated with olivine at high pressure and temperature? Seemingly so. This is one reference that will allow me to do that. Say 1500 C and 1.8 GPa is not an unreasonable pressure and temperature for an area around a mantle plume. So that part's reasonable. The other part is, gotcha, that there are terrestrial analogs for these rocks. Of course, there's the famous Theos flow that Rachel Friedman Lentz wrote about many years ago up in Canada. There are also other pyroxenites which are not cumulates, and this is an uncaramite. Thank you to Hillary Downs for the picture. This is a lava. This loaded with pyroxenes, but it's not a cumulate. Okay, so I will just do one more thing here with this wonderful data set that Udry and Dave put together. Looked at the trace element content of the pyroxene cores, which should be the first minerals that are crystallized from these magmas. And what you see there is, like, say, samarium. The amount of samarium in the pyroxene cores correlates very, very well with the bulk samarium in the magma. So what's happening here is these pyroxene cores are growing from the magma depending on how much samarium is in them. So the samarium, this extra trace element content that was added before the pyroxene cores grew. And that suggests to me that it's probably a mantle thing rather than a crustal assimilant. So I have just 30 seconds left, and that should allow me to summarize. Most of this is summary that I already said, but the one cool thing that's left over is that if you have pyroxenitic magmas, you really have to have peroxenite in the source region. There has to be a bunch of pyroxene down in the source region to make this. And of course, we have peroxenites in the Earth's mantle, and I've got this picture of mantle xenoliths from Peridot Mesa, Arizona. This is a pure peroxenite xenolith, and here's a peroxenite veinlet cutting of peridotite. And I don't think that the presence of peroxenites in Mars's mantle has really been considered, and I think that this work suggests that it ought to. 9, 11, oh, I'm over by 12 seconds. I'm sorry. I'm done.
All right, thanks, Ellen. Our next speaker will be Sierra Ramsey, discussing some insights into how knockalites are in place. Go ahead when you're ready, Sierra. Thanks.
Okay, so knockalites are going to be clinopyroxene-rich cumulate-like rocks. My slide isn't up yet, but if it was, you would see a backscattered electron image of, let's see, there we go, of what we expect the mineralogy in a typical knockalite to look like. So we have clinopyroxene, olivine, plagioclase, iron, titanium oxides, and in some samples we'll have a glassy material as well. The knockalites also have shared crystallization and ejection ages. The narrow range of crystallization and shared ejection ages leads us to believe that they were ejected from the same location on Mars at around the same time. So with 32 samples, they're the largest single origin suite of rocks that we have from Mars. And because we do think they're from the same location on Mars, we can study them in a manner similar to how we would study terrestrial rocks. And so this includes Martian magnetism processes like emplacement processes and environments, which are still not well understood. So without relevant geographic and geologic context, it's uncertain whether the knockalites represent intrusive or extrusive rocks or a combination of both. Previous studies have suggested they could be from thick lava flows or shallow intrusions. And so to help resolve this uncertainty, we can use X-ray computed tomography or XCT to help better constrain where the knockalites were emplaced relative to the Martian surface. And so going into this study, we had a couple of goals, which included using X-ray computed tomography or XCT to conduct true 3D crystal size distributions or quantitative textural analyses. We also wanted to be able to delineate how and where the knockalites were emplaced. So are they intrusive, extrusive, and can we say where they might have solidified in, such as the shallow intrusions or a lava flow or another type of environment? And then we also wanted to be able to compare them to the previously proposed terrestrial analogs like Alan mentioned with Theo's flow. And so, is it going to play? Oh. So X-ray computed tomography, or XCT, is a non-destructive analytical technique that can be used to visualize the internal structure of rare and precious samples like Martian meteorites. And so to the bottom left is just a little schematic of an XCT setup. On the bottom right, it wasn't working, but that should have been a video of Northwest Africa 10645 walking through. And then XCT also allows us to assess variations between 2D and 3D, and sometimes we're able to see textures that might be absent in thin section, as well as making direct measurements for crystal size and orientation. So for our study, we conducted XCT scans on a total of 8 noctilites. And for all of those, we conducted 3D and 2D modal abundances. And then for a select number of them, we also conducted 3D crystal size distributions, so our quantitative textural analysis and a petrofabric analysis. And so after our XCT scans are acquired, the first thing I do is segment the data using machine learning in a program called Dragonfly. And so this is where we assign our phase or phases of interest a specific or range of grayscale values that we can then isolate. And so on top here is a raw XCT slice. It's really similar to a backscattered electron image of Northwest Africa 10645. And we can think of this as just one single thin section from this scan. On the bottom is that same slice after it's been segmented. And so with that segmented data, I can then calculate the modal abundances, both on a 3D whole rock volume basis and on a 2D slice by slice, or essentially thin section basis. And so to break down what we're seeing here in this plot, the X's are going to denote the 3D whole rock volume percent for each phase. The center of our boxes are going to be the 2D averages from thousands of slices, plus or minus 1 standard deviation. And then the full line is the full extent of the measured range for our abundances. I do also want to note that the mesostasis for the Miller range noctilites also includes skeletal oxides, because they cannot be confidently segmented on their own. And so what we see is that the 2D and 3D modal abundances for the noctilites is variable, both in 2D and 3D. And this is pretty consistent with what previous studies have found when they looked at thin sections. What was interesting and unexpected, though, is that Miller range 090032, which is highlighted here in the center in this purple box on the right, has considerably less pyroxene and more glassy mesostasis than the other Miller range noctilites, which is a proposed pairing group. So next we can look at our crystal size distributions, or CSDs. And so our CSDs can tell us a lot about the overall thermal and kinematic history of magmas, and includes things like growth rates and residence times. Traditionally, our CSDs are conducted in 2D on thin section and then rely on a stereological conversion to obtain our 3D crystal shapes and sizes. But as you can imagine, this conversion can introduce error that then gets propagated in subsequent analyses, especially as our crystal shape deviates away from a perfect sphere. And we also have a question of if the thin sections that were used in the previous analyses are actually representative of the bulk rock they had been cut from. And so to overcome all of this, we can do our 3D crystal size distributions. And when doing this, I oriented the CT scan to find the long axis of each pyroxene crystal within a specified subvolume within our samples. And so once I found the long axis, I drew a rod, which you see here on the left in blue, along the center of that long axis. I did that for all the pyroxenes within that subvolume, and then extracted the crystal length and the crystal orientation using a program called Blob 3D, which produces these little figures like you see in the middle that I fondly refer to as hot dogs. And then once we have all that information extracted, we can construct our crystal size distribution plots seen here on the right. And so here are our 3D crystal size distributions for the noctilites in our study. On the right, we have crystal size, or crystal length in millimeters on the x-axis, and the natural log of the population density on the y-axis. So we can think of our CSD plots as like a modified histogram. On the right, we have another little plot where we have CSD slope on the x-axis and CSD intercept on the y-axis. So overall, our CSDs slope and intercepts for the noctilites are pretty similar. The only exception is Lafayette, which from its steeper slope indicates that it could have cooled a lot quicker than the other noctilites, which are more similar to one another. We can also look at our y-intercepts for our CSDs, and we see that they're relatively high. And so a high CSD intercept corresponds to a high nucleation density in our magma. Such high nucleation densities can be caused by effective degrees of undercooling, which is also consistent with Oswald et al. 2024 work, where she observed undercooling as an important process in the crystallization of noctilite cumulus phases like pyroxene and olivine using incompatible and trace element maps. The other thing to note with our CSDs is that we observe a flattening of our profiles around that 2 to 2.5 millimeter mark, with the exception again of Lafayette, which we think might be indicating that we're seeing a magma recharge event. And so lastly, I would like to address our petrofabric analysis. But before I show you the results, I want to briefly go over the types of fabrics that we can see. The very first can be no fabric or a random fabric. So this can be a result of in situ crystallization. And in this case, our pyroxene long axes or C axes, when we plot them on a stereo net, they're not going to form a girdle or anything that looks like a belt, and they're not going to be clustered together either. Next, we can have foliations, which are going to be planar features that are associated with some sort of compressive stress. This can happen during crystal accumulation and a shallow intrusion like a sill or a dike, as well as in the flattening regime of lava flows. And on our stereo net, we're going to see a girdle in our long axes that represents the plane of foliation. Lastly, we can have lineations. So this is going to be more associated with simple shear, so some type of more prominent flow, which can occur at the interface of a crystal mush in a magma chamber, as well as the flow direction in an extrusive lava flow. And on our stereo net, our long axes are all going to be clustered together. Keep in mind, this is schematic, and our real data does not look quite this nice or straightforward. But when we do plot the pyroxene long axes for the noctilites, we see there is a fabric present. There's a foliation present that, again, corresponds to that flattening of magma that we can get via pure shear and crystal accumulation. And so we have a range of fabric strengths, with the strongest fabric being Northwest Africa 10645 on the upper left and the weakest Miller Range 09002 on the bottom right. And so these fabrics can be produced in both intrusive and extrusive environments and are also consistent with what studies that have used EBSD has found as well. And so to wrap things up, we see that our modal abundances in both 2D and 3D are quite variable for the noctilites, which is consistent with what previous studies have found. We also see that undercooling based on our CSDs is likely a really important process during the formation of noctilite pyroxene, which is consistent with Ostwald et al.'s 2024's work, suggesting that it's an important process during noctilite formation and crystallization. We see evidence of potentially a magma recharge event with our CSDs with the flattening of those profiles. We also see that our petrofabrics are pretty consistent with what's been found with EBSD studies. So when we pull everything together from our study with our 3D data, EBSD studies, and studies that have looked at detailed bulk and mineral chemistry, it's clear the noctilites have a really complex formation and emplacement history. So any and all the environments you see here on the left could have produced the noctilites. But texturally, at least from what we see with our CSDs and our petrofabrics, indicate that there was some degree of crystal accumulation during their solidification. And with that, thank you for your time and attention.
Thanks, Sierra. Our next speaker is Amanda Ostwald, who will be diving into some diffusion and zoning profiles in olivine and other phases. So thanks, Amanda. Go ahead when you're ready.
Thank you. Hi, everyone. I'm Amanda. I'm a postdoctoral fellow at the Smithsonian National Museum of Natural History. And I'm going to be talking about one of the cool samples we have in our collection. It's elephant moraine 79001. This was collected during the 1979 Antarctic Search for Meteorites expedition. It is a really important meteorite in our collection because it's one of the very few that has a contact between two different lithologic units. So we're looking at two different types of rocks in one stone that are in contact with each other, so we can study two different geologic processes in one coherent sample. The two different lithologies, we don't really know how they relate to one another. They are gradationally related along the contact in a microscope, but in hand sample, it's really obvious what the distinction is. So the first lithology is the largest by volume in our rock. It's lithology A. It looks a lot like the olivine ferric shergottites. So it's got this fine ground mass of pyroxene and maskelinite, which is a shocked plagioclase. And then it also has these really large megacrystic phases of olivine and pyroxene. And the second lithology we call lithology B. It's very similar to basaltic shergottites. So it's this coarse-grained sample with pyroxene and this lathe-like maskelinite, some whitlockite, apatite, some mesostasis. And then we have a kind of informal lithology, lithology C. This is used to describe any of the melt glasses that are kind of scattered throughout the sample. Importantly, the shock melt in this sample contains gas that is identical to the gas in the Mars atmosphere as sampled by landers. So this was our very first smoking gun meteorite to prove that we had Martians among us. And again, it was collected by ANSMET, which is an incredibly important program to our understanding of cosmochemistry and the evolution of the solar system. It's a very cheap form of sample return, just as a pitch. So again, like I said, those two lithologies, A and B, we don't totally understand what the relationship is toward one another. And the biggest problem is that lithology A, those big megacrystic phases, might not have actually formed with the rest of the rock. And so just to revisit, again, we have this fine-grained ground mass of pyroxene and mescalinite, and then these really large grains of olivine and pyroxene. And the first option for how this formed is that olivine and that pyroxene, those big megacrysts, actually formed in separate magmas. They cooled, and then they were pulled up into a fresh magma that formed the rest of the ground mass. And in that case, those megacrystic phases are xenocrystic. The second option is that only a very small portion of those megacrystic phases are actually xenocrystic. They actually formed together in a magma, the olivine and the pyroxene megacrysts, and then they kind of shot up through the crust and they formed this finer grained ground mass. In this case, all of these phases would be phenocrystic. But we've developed some new methodologies to study how minerals form relative to one another by looking at a process called zoning. And so we wanted to look at some of the zoning in these grains between lithology A and lithology B and see if we couldn't deduce some of that history a little better. So to explain zoning, we're going to dive into a magma chamber. We're going to start forming olivine. Olivine will incorporate first the elements which are compatible in the crystal structure. So magnesium, it'll be a little bit elevated when we first start forming. And then as we pull magnesium out of our magma, we'll enrich the magma in other elements. So we might continue to form olivine and it will be enriched in iron. And this is the foundation of zoning. It's a difference in the distribution of chemical elements through your mineral grain to represent some change, be it chemical or physical, in your magma. If you let this sit under elevated temperatures, magmatic temperatures, for enough time, the iron and magnesium will start to switch places in the crystal lattice in a process called diffusion, so that zoning gradient will be relaxed. And given enough time, it will approach homogeneity throughout the grain. And for iron and magnesium, this happens really quickly, on the order of like tens of years. But if we look at other elements, they diffuse much more slowly in these mineral grains, and they can preserve that initial formation condition. So for olivine, for instance, we can look at elements like phosphorus. It diffuses very slowly. In this terrestrial olivine from the Reunion Island basalts, we can see where phosphorus is enriched, the olivine grain grew really quickly. And then in pyroxene, we can look at elements like chromium, aluminum, titanium. In this Hawaiian oncaramite pyroxene, it grew really rapidly wherever chromium is enriched. And then to do this mapping, we used the electron microprobe at the Smithsonian. We also used the laser ablation inductively coupled plasma mass spectrometer at the University of Delaware. I've done some chronometry on this, but I still need to do some EBSD to correct for crystallographic orientation. That's a different story. We're going to focus in on some of the zoning results for today. All right, so this is one of my olivines from lithology A. That's that olivine ferric lithology. I have a backscattered electron image on the left, and on the right is a compositional map where calcium is in red, magnesium in blue, and iron in green. We have a melt inclusion central to the grain, and melt inclusions are usually incorporated when minerals grow really rapidly. So I was hopeful for some really cool zoning in this. I was disappointed. I also see some orthopyroxene inclusions in the central part of my grain. And that orthopyroxene is the same as my megacrystic pyroxenes in this sample. And then I see some zoning toward the rim where magnesium's a little depleted, iron is a little enriched. When I start looking at my slowly diffusing element maps, I've got calcium in red, or calcium on the left and phosphorus on the right. And these are heat maps where higher concentration elements are warmer colors like reds and lower concentration elements are cooler colors like blues. My calcium and my phosphorus seem to be like cross-cutting against each other, like these, where enrichments are like forming these veins that are straight lines through the core. This is likely not original zoning. This is likely, these are just following some veins through the structure of the crystal. But I also see some enrichments of calcium and phosphorus at the rims. But when I pull out my laser maps, I see a lot more detail. So I have, these are heat maps, again, with magnesium, calcium, and titanium. And again, I can see some magnesium depletion around the rim correlating with some calcium enrichments. It's a little diffuse. With the laser, I can actually look at a lot more analytes than I can with the microprobe. And so I looked at titanium, which is a little unusual. And I did see some really sharp titanium enrichments on the outer rim of this olivine. And this is kind of strange because I said that olivine should have been crystallizing at the same time as pyroxene, but calcium and titanium are much, much more compatible in orthopyroxene and in glinopyroxene than they are in olivine. So likely that is not the case. Likely this olivine was forming separately from pyroxene, at least in the later stages. And what's even more interesting is that titanium can be incorporated into olivine and terrestrial olivines in two ways. It can either take the spot of silicon in the crystal lattice. I don't see that happening because silicon is very homogeneous in this grain. Or it can take the spot of magnesium if it couples with hydrogen in a hydrous magma. So that's kind of exciting. This might be indicating that we've got some kind of hydration in our magma in the late stage. You guys might be wondering, if you're oxygen vivacity experts, if that might mean that there's a change in the oxidation state of my magma, if there's some kind of hydroxyl ion floating around. And it looks like that is the case. So when we look at some of our redox sensitive elements like chromium and vanadium, we can see that there is depletion along the rim. The cores have kind of a spotty texture, and past authors found that this is because they might have formed under reducing conditions. It might have been more homogeneously distributed. And then during some late stage oxidation event, those phases, those like microcrystalline phases exolved out, taking the chromium and vanadium with them. But we do not see those phases in the rim. So this continued to form under oxidation, an oxidative environment. Oh, that's not great condition looking. Okay. So we're going to look now at our pyroxene. We've got a backscatter electron image on the left and then a titanium heat map on the right. My titanium heat map shows that this is one of my pyroxenes from lithology A. This is my olivine pyrric lithology. It's very patchy, very irregular. It might have formed really rapidly. And when we look at my pyroxenes from lithology B, again, that's my coarse basaltic lithology. I again see a very patchy zoning. If I can put these side by side, you'll see that they look very similar. So these are these two different lithologies, these very large pyroxene grains, and both of them seem to be forming under similar thermal conditions or similar physical conditions in my magma. So that's a connection there. So if I can wrap this all up together, I cannot make any good conclusions about the petrogenetic history of lithology A. Unfortunately, our olivine got much more complicated. Likely those rims of those olivines did not form at the same time as pyroxene was forming because they are enriched in elements that should have been enriched instead in the pyroxenes. What's more, there was some kind of late stage oxidation event that might have been concurrent with some kind of hydration event in the magma. But there are still orthopyroxenes inside of the core of the olivines, so I don't totally know how these are relating together. But one thing I can provide is a little bit more of a constraint about the history of lithology B, and that is that the pyroxenes from both lithology A and B seem to be forming under similar thermal conditions. But the best way to resolve the problems with lithology A and the connection, again, is by doing some more analyses, ideally with the laser, and resolving micronometry. Thank you.
Thank you very much. The next talk in the session is on the stratigraphy of the poikilotic sugartite igneous body. And the talk will be given by Sojiro Yamazaki. Whenever you're ready, please go ahead.
My name is Sojiro Yamazaki from University of Tokyo. Today, I'd like to talk about crystallization of poikilotic shagotite. Shagotite is the largest group of Martian meteorites. Analyzing these samples allows us to investigate Martian past magmatic crystallization processes. Shagotite can be classified into these three major subgroups. Each group is believed to have formed magma with varying degree of differentiation or through distinct crystallization processes. In this study, we focus on poikilotic shagotite. Shagotite can be classified into these three geochemical subgroups by distinct geochemistry, which is independent from petrological classification. These three geochemical classifications are thought to reflect the differences in the mantle source of the magma from which shagotite originated. This slide explains the formation process of polychaetic shagotite. First, mantle partially melted and formed deep magma reservoir. Olivine and pyroxene crystallized there, and pyroxene formed the texture surrounding olivine. This texture is called the polychaetic texture and became the name of polychaetic shagotite. Finally, it is believed that the magma intruded into the crust near the surface and solidified, forming the polychaetic shagotite. This is a typical texture of polychaetic shagotite. In this magnesium map, the area from yellow to red is olivine, green to blue is pyroxene, and the black area that fills in between the crystal is masculinite, which is amorphous proteoglyphs. The area pyroxene surrounds olivine pale region is a polychaetic texture that I explained in the previous slide. NP region has a non-polychaetic texture. Also, looking at calcium map, we can see that large pyroxene consists of a calcium core and a calcium-rich rim. In recent years, as the numbers of polychaetic shagotite discovered polychaetic shagotite increase, it has become clear that there is diversity in petrological texture and mineral compositions. However, there are a few detailed descriptions of new samples. Also, the final magma crystallization process of polychaetic shagotite has not been discussed in detail. Therefore, we aim to constrain final magma crystallization process of polychaetic shagotite by analyzing and comparing the petrological texture and mineral composition of 10 polychaetic shagotite. These are samples we analyzed. We analyzed petrological texture and mineral composition by electron microscope. We also conducted ion microzanes analysis to evaluate redox state of projects. Next, let's talk about the result. Shown here are the magnesium maps of 9 analyzed samples except RBT. The top 5 are intermediate samples and bottom 3 are initial sample, and this is a depleted sample. As for the petrological texture, it can be seen that a polychaetic region is present enclosed by the white dotted line for all samples. Also, looking at calcium map, we can see that large pyroxene consists of a calcium core and a calcium-rich rim. Next, I'll introduce the mineral composition starting with pyroxene. No significant compositional differences are observed among the samples for pyroxene's major elements. Previous studies have proposed that the formation depth of pyroxene can be estimated based on the aluminum-titanium ratio. Using this diagram, it is estimated that pyroxene's core and rim plotted in purple and green is formed near the mantle crust boundary. In contrast, the sample plotted the pyroxene in the non-polychaetic texture plotted in light blue are estimated to have formed in a relatively shallow region near the surface. Next, I'll discuss the olivine composition. The Forsyth number in both polychaetic and non-polychaetic texture were plotted for each sample. From this figure, it can be seen that these 3 samples exhibit relatively large compositional differences between polychaetic and non-polychaetic texture. So it is suggested that these 3 in general, the faster the cooling rate is, the wider the compositional range is. So it is suggested that these 3 samples experience relatively rapid cooling during the formation of the non-polychaetic texture. Additionally, these 6 samples exhibit narrow. For these 6 samples, the narrow compositional range suggests that non-polychaetic texture formed through thorough cooling. The major elements of masculinite also shows a similar compositional tolerance similar to that of olivine. We also analyze ion valence state of masculinite The iron 3 plus to total iron ratio is plotted here for each sample. From this figure, it is suggested that from this figure, you can see that there is a weak correlation between geochemical classifications and iron valence state. So it is suggested that enriched chalcotite formed from oxidizing magma, depleted chalcotite formed from reducing magma, and intermediate chalcotite formed from magma with an intermediate redox state. So this may imply that the redox condition depends on the redox state depends on the difference in the source magma. Next, I'll explain the method to estimate the cooling rate by focusing on the titanium diffusion profile. Pyroxene crystals are thought to are estimated to have formed in a deep magma reservoir. When the magma containing these pyroxenes are intruded into the crust and crystallization process of olivine, pyroxene, and plagioclase proceeded, the titanium concentration and melt increased as these minerals crystallized. This led to a metal diffusion between titanium-rich melt and titanium pyroxene, and the pyroxene rim to become enriched in titanium. Shown here, as an example, here is a titanium diffusion profile for NW 12241. Using the metal diffusion equation, the cooling rate was estimated to be about 0.17 degrees Celsius per year to reproduce this profile. In the same way, cooling rates were estimated for other samples as well. In this graph, here we plotted the obtained cooling rate on the horizontal axis and the molar abundance of muskinite in non-polychaetic texture on the vertical axis for each sample. Because plagioclase tend to crystallize in the later stage, the proportion of muskinite in non-polychaetic texture reflects the effect of the accumulation of other crystals. From this figure, we can see that there is a correlation between cooling rate and accumulation degree. Considering this correlation, we propose a igneous body of polychaetic chalcotite as shown here. If universally the similar igneous bodies existed on Mars, the differences, regardless of the difference in the source magma, the sample plotted in the blue region could have formed from magma that intruded into the crust and solidified quickly near the margin of the intrusive magma. In contrast, the red region samples likely have formed in a central region of the intrusive magma. The sample estimated how the lowest cooling rate is assumed to have formed in a central region. We using the thermal diffusion equation from 1200 to 1000 degrees Celsius, the size of the polychaetic chalcotite igneous body was estimated. Here we assume that the magma intruded into the crust near the surface as a form of the thick seed-like body. Using the thermal diffusion, then the size of the igneous body was estimated about 270 meters. Here is the conclusion. Thank you for your attention.
Okay, our next talk is on magmatic oxygen fugacity from experimentally calibrated vanadium oxybarometry by Sophie Benaroya. Oh, thanks.
Thanks for that introduction. So hi, everyone. I'm Sophie, and I'm a PhD candidate at the University of Alberta. So I wanted to start by talking a bit about what oxygen fugacity, or FO2, is and why it's important. So FO2 is a measure of the chemical potential of oxygen in a system. And it's important in determining what minerals are thermodynamically stable over others at certain conditions, so like high, medium, or low FO2. FO2 also influences volatile speciation, and it can help us better understand processes like magma mixing and volatile degassing in the interior of Mars. Now, since the absolute oxygen fugacity in a system is real small, it's more practical to talk about it in log units relative to a mineral redox buffer, like the QFM buffer, which is the one I'll be talking about today. So for sugartites, most FO2 estimates come from using iron oxybarometry. So two of the most popular ones are the olivine orthopyroxene spinel oxybarometer, which uses those three minerals to estimate FO2, and it's typically applied to poikilotic and olivine ferric sugartites. The second uses the minerals ilmenite and titanomagnetite to estimate FO2. These are later crystallizing phases, and so they give us late stage FO2 estimates. Given that basaltic sugartites lack primitive olivine, only this second oxybarometer has been applied to samples, leading to questions about their magmatic FO2. So my supervisor, Chris Hurd, and I recently submitted a paper compiling sugartite FO2 values, and the plot here is a summary of some of that work. So I have sugartite FO2 values against their lanthanum and ytterbium ratio. I've also plotted here our estimate for the FO2 evolution of the Martian mantle. This is the magmatic FO2 that sugartites would have had. And that's the solid black line. The dashed lines on the other side are a standard deviation from the average. So you'll notice by looking at the early FO2 estimates for olivine ferric sugartites, which are the blue squares, and poikilotic sugartites, which are the blue circles, most of those points plot in between these lines. But basaltic sugartites, which are represented by the red triangles, plot on the more oxidizing end of this graph. Again, raising the question, are these magmatic FO2 values or later stage FO2 values? So to me, it's clear from this plot that we're going to need a different oxybarometer if we want to try to figure out the magmatic FO2 of these samples. So an alternative is using vanadium as a redox indicator. Vanadium, as has already been discussed, exists in multiple valence states. Those of which that are most applicable to Martian studies are vanadium 3+ and 4+. That's because the sugartite FO2s range from around QFM -4 to +1 or +2. Now, as the magma oxidizes, there's going to be less of that vanadium 3+ in the magma and more of the vanadium 4+. Since the 3+ state is preferentially incorporated into olivine and pyroxene, we can use the vanadium partitioning in these minerals to estimate FO2. Now, this has been done for many terrestrial calibrations, and some of those calibrations have been applied to olivine ferric sugartites. An issue with doing a vanadium-only oxybarometer using that to estimate FO2 essentially, is that you need to know the vanadium content of both the mineral you're interested in and of the melt. And the sugartites are, crystalline. So that's a little bit of an issue. A possible solution to the no melt problem is to normalize vanadium to a trace element that is homovalent, has the same charge, and is unaffected by changes in redox. So a bunch of elements have been looked at as a potential normalizer, things like scandium, yttrium, and ytterbium, with scandium emerging as the best candidate because it's the most similar geochemically to vanadium. So you would then take this ratio as a sort of redox proxy. Now, all of these homovalent trace elements, they're all going to form charged coupled substitutions with aluminum and sodium. What that means is that plagioclase could affect their partitioning. So that's a big question remaining, and we also aren't sure how applicable some of this work is to sugartites because they're pretty different compositionally from the terrestrial rocks or experimental charges from the past. So to try to calibrate a vanadium X oxybarometer for sugartites, I ran so many experiments. I used the composition of basaltic sugartite, QUE 94201, which is thought to represent a fractionated mantle melt. I doped that with vanadium, scandium, yttrium, ytterbium, and zirconium. And I put that doped mixture in vertical gas fixing furnaces over at the U of A and put that at a set FO2 and temperature for a couple days. When I took those samples out and mounted them, I used EPMA to analyze the resultant phases. So in the red square, you can see that pyroxene and olivine crystallized and there's abundant glass. Since, again, basaltic sugartites don't have primitive olivine, I'm only going to focus on the pyroxene for the rest of this talk. So shown here is a pyroxene quadrilateral. All of the bright points represent my experimental pyroxenes. I've also plotted here the composition of QUE 94201 from the literature, as well as some data for basaltic sugartites that I later applied my oxybarometer to. You'll notice that all of my experimental pyroxenes plot in the augite region of the QUE mantle portion, essentially telling us they're augites, and so any work I do with these pyroxenes can only be applied to other augites. After using EPMA to analyze these samples, I used laser ablation ICP-MS to get trace element data on the partitioning of the different trace elements. So shown here on the left is a plot with the FO2 at which I held these pyroxenes at against their partitioning or d-value between pyroxene and melt, or glass in this case. You'll notice, unsurprisingly, that vanadium partitioning decreases with increasing FO2. That's because more of that vanadium is going to be in that 4+ state, which is really incompatible in pyroxene. Now, for a normalizing agent, I want one that's unaffected by changes in FO2, so one where this line stays flat. So that best describes scandium. The other trace elements show a slight increase in compatibility with increasing FO2. So after going through this data, I decided to plot up the vanadium-scandium ratio against the FO2 of these pyroxenes to look at that relationship. And it's great, it has an R-squared value of 0.95. So I decided to use this as my new vanadium X oxybarometer that I then wanted to apply to 4 basaltic shergottites in our collections: NWA 16367, 12919, and 10299, as well as JAH 479. Please ignore the reference, shouldn't be there. This is all my data. But anyways, to find good points to apply this barometer to, wanted to make sure I was hitting the cores of my pyroxene. So I did elemental mapping of all my samples. A combo iron, magnesium, calcium map is shown here. And the pyroxene cores are the orangey red color. Now, my laser ablation spot size was a little smaller than 100 microns, which is that white dot there. So I wanted to make sure I was looking at areas that were larger than that white dot, essentially. After I got that data, I wanted to check if scandium was fractionating in these natural samples, even though it didn't appear to do so in my experiments. And you'll see on the plot on the right where I have pyroxene magnesium number against scandium concentration. There's a lot of scatter in the graphs, but not a lot indicating that scandium was being preferentially incorporated into any of these pyroxenes. So shown here is the graph I showed before. It's in grayscale now. I have the FO2 of shergottites against their lanthanum and ytterbium values. As a reminder, the basaltic shergottites plot towards the more oxidizing end of this graph. And here's my data. So all 4 of the shergottites that I looked at had previously had their FO2 estimated to be around QFM -1. The new vanadium scandium oxybarometry results indicate that their FO2 is around -1.6 to 1.7. So these are the most magnesium-rich pyroxenes that I've decided to plot here. But if I plot all of my data, you'll see that there's a much wider trend, I guess. Sorry about that. And one thing to note is that these more oxidizing values are correlated to pyroxenes with lower magnesium numbers. So yes, they show oxidation, but oxidation with an evolving melt. So these more oxidizing values from iron FO2 estimates are likely recording these more oxidizing values towards the end of the sample's crystallization sequence. So to conclude, I've developed an empirical vanadium scandium oxybarometer for augites in basaltic shergottites. I applied it to a bunch of samples, and they appear to have a more reduced magmatic FO2 than indicated by previous iron oxybarometry estimates. That's telling us that maybe those iron-based oxybarometers are giving us slightly too oxidized values for the basaltic shergottites, at least in terms of their magmatic FO2. That being said, more experiments are always needed, and I'm running them. I'm looking at experiments at higher temperatures, as well as slow cooling experiments to look at the effects of plagioclase crystallization, because I couldn't form any this time around. I'm also looking at the effects of pyroxene zoning, and I'm also testing additional compositions to try to make low calcium pyroxene and olivine vanadium scandium or vanadium X oxybarometers to apply this work to other sample types like olivine ferric and poikilotic shergottites. So there's a lot more data coming in the future, so please stay tuned, and thanks so much for your attention.
Thanks very much. And the last talk in the session before we have the panel Q&A is SNC meteorites indicate a chondritic origin for krypton in the Martian mantle. And the talk will be given by Christian Kromer. Whenever you're ready.
Laser pointer. And okay, cool. That's how we change slides. All right. So hello, everyone. I'm going to start off with more of just a broad question about where do planets actually get their volatile elements from, your oxygen, carbon, hydrogen, and such. And generally, you can get them from two broad reservoirs. One might be accumulating them from the solar nebula as the planet's forming. Alternatively, you might have chondritic impacts where chondritic volatiles are being delivered to the planet. But the problem is that these elements are then modified by physical, chemical, and maybe biological, who knows, processes that are going to be moving these elements around the planet in a lot of different ways that we have to end up accounting for. So what we've done is use noble gases for tracking these volatiles as they travel through the planet. And the benefit of that is that because they're inert, we can mostly just focus on the physical processes. In particular, for this research, krypton is really important because there's a particular distinction that we can make between the solar and chondritic compositions. All right. So I did mention before that all these volatiles do move through the planetary system. And so related to that is, how do planets build their atmospheres? Because the traditional idea has been that you have a primordial atmosphere that's formed from the solar nebula, and then that gets stripped away by hydrodynamic escape in the early ultraviolet radiation environment of the early solar system. Then subsequent to that, you have outgassing from the interior that produces a secondary atmosphere that is then modified to create the present day atmosphere that we see 4.5 billion years later. So when we look at Mars's current atmosphere and its krypton isotopes, it has a solar krypton composition. So logically, if that is outgassed from the interior, then the interior should also have a solar krypton isotopic composition. Hopefully that's not too much of a stretch. And so then it comes to, well, let's test that. Let's take a representative of the Mars interior and actually see, does it give us a solar krypton isotopic composition? Now, luckily, this is the only plot that I'm going to use for my entire presentation, so that means I can get into the nitty-gritty details. On the vertical axis, we have Krypton 86 over Krypton 84. This is the primary isotopic measurement that we're using to differentiate between our solar and chondritic compositions. So for the solar composition, we have solar wind, which is this orange star. Hiding right underneath it is a blue square that is our Martian atmosphere composition. So just to make the point of how similar they are. Then we also have our chondritic composition. So we've got the average carbonaceous chondrite as a blue star and the phase Q composition as a purple star, which are around 0.31 for the people who are online. And those are nicely hidden underneath a lot of those blue dots. Don't worry about those right now. And then in between, just for reference, we also have Earth's atmosphere as this black square. The one issue is that Krypton 84, when we look at the Martian meteorites, is affected by cosmic ray interactions. And so we need to find a way to account for those cosmogenic interactions. And that's where, on the horizontal axis, we have Krypton 83 over Krypton 84, with Krypton 83 being the isotope that is most commonly produced by these cosmogenic interactions. So that end member is down off the edge of the screen, somewhere through the floor. We don't really care that much about where exactly it is, but the point is that we can draw mixing lines between that cosmogenic end member and a solar composition or a chondritic composition. So let's take a meteorite that's representative of the Martian interior, like Chassigny, and we're going to step heat it. That way we can focus on particular components within the meteorite. So at the lower temperature steps, we're getting mostly cosmogenic material. But then as we increase the temperature, we start slowly creeping up towards a chondritic composition, not a solar one. And we can actually extend this for the Chassignite reservoir as a whole because of some recent measurements that were just recently published for Northwest Africa 8694. But it's important to keep in mind that there's a lot of recent research that's indicated that there's probably a lot of interior heterogeneities in the Martian interior that have been persistent since its early differentiation. And some of these do apply to volatiles. So maybe we make the argument that Chassigny and the Chassignites are part of an anomalously chondritic reservoir, whereas the rest of the Mars interior, or at least what was primarily outgassed to form the atmosphere, is predominantly solar. So to actually determine whether that's the case, we're going to look at a bunch of different meteorites across several different groups. So for the research that I'm presenting, we looked at one Noclite, Lafayette, two enriched Shergottites, Los Angeles and Zagami, and then one intermediate Shergottite, ALHA 77005. And all of these meteorites were studied using infrared step heating. And then once the gases were released from the meteorite at each temperature step, the noble gases were separated using a dual cryogenic system. And then for each noble gas at each temperature step, they were measured in a new generation of Noblesse HR mass spectrometer. And so what do we find? Well, I'm going to take you back to the same plot that I showed you before, right? We've got, again, our Krypton 86 over 84 on the vertical, 83, 84 on the horizontal. There's our Mars atmosphere and solar composition. We have our two chondritic compositions, again, ABCC, or carbonaceous chondrite, and phase Q, which is sort of more non-carbonaceous chondrite. It's complicated. And then in between, again, Earth atmosphere, as well as our two mixing lines, chondritic and cosmogenic mixing line, and solar and cosmogenic mixing line. And just for familiarity, Chassigny has also been plotted. So again, our low temperature steps that are leading up towards the chondritic compositions. And then I plotted the data for ALH 77005, which again is our intermediate Shergottite, which within error all generally plots around that chondritic composition. In fact, the weighted mean is just slightly more cosmogenic than the chondritic composition. And so that would suggest that this is an entirely separate reservoir, yet it has chondritic krypton in it. And here's including all of the meteorites that I've thus mentioned so far. So we've sort of condensed it down, make it a bit more simple, where we have low temperature steps as the circles and high temperature steps as the squares for each meteorite. Just to basically break it down, Zagami, one of the enriched Shergottites, shows a very similar trend to Chassigny and ALH, again, falling along this chondritic cosmogenic mixing line by and large. And then Lafayette and Los Angeles, well, those two are a bit more complicated because with those two, it seems like they're having a lot more interaction between maybe more cosmogenic interactions, maybe some terrestrial contamination. There might be some Mars atmosphere contamination, or maybe even some indications of a solar source for the Mars interior. But all of that kept in mind is that none of these really seem to show, none of the SNC meteorites that we analyzed seem to show a consistent solar signature that would be consistent with the Mars atmosphere. And okay, well, it's been 4.5 billion years, so maybe the atmosphere loss from Mars has taken the interior gases and fractionated them to where they are in the atmosphere now. And well, that doesn't really quite work because if we consider mass fractionating atmospheric loss, your Krypton 86 over 84 ratio is going to get heavier. You're going to move farther away from what we actually observe in the atmosphere. So all in all, that means that what we're looking at is that most of Mars's interior reservoirs seem to show something resembling chondritic and almost certainly not something purely solar. And that means that we can't produce the Mars atmosphere strictly by outgassing, either during a magma ocean phase or by extensive volcanism. And so this also has implications for the time periods in which Mars forms. If you need to have the solar nebula present and chondritic materials present to be able to fill up the interior with chondritic krypton, but then you need to have some solar source, whether that's a planetesimal or maybe cometary source, or potentially the solar nebula itself still persisting during Mars's formation. And so that might limit the accretion time to less than 4 million years potentially, so that you have the solar nebula present to be able to create Mars's modern atmosphere that then subsequently gets modified. So a little food for thought for everyone. Hope you enjoyed.
Thank you very much. Christian, don't go too far away. You're going to be up on the stage here along with the other speakers from the session. If you can make your way up, and then if you have a question, please come to one of the microphones at the front, and remember to state your name and affiliation. And we will also monitor online. So just give people a moment to settle in. Okay, at the microphone here, go ahead.
Hello, great talks, everyone. This is Michael Phillips from the University of Arizona. My question is for Alan. He can his head around there. That was a really intriguing talk. Thanks for that. And you mentioned in there that you think there might be a pyroxene source in the mantle. My question is, do you have any constraints on what flavor of pyroxene, specifically calcium content?
Well, the fact that, am I on?
Yeah, we can hear
Yeah,
you.
the fact that the knocklights are clinopyroxene rich rock suggests that it's a clinopyroxenite mantle. But beyond that, I don't have any, my thoughts haven't gotten that far yet. I think just the thought that there might be pyroxenites as an important part of the Martian mantle is, I think, pretty new, and I think that's an important thing. But beyond that, I don't.
Okay, that's great. And I have a plug. Come see my talk on Thursday, where I think I'm seeing observational evidence of clinopyroxenes in mantle material around the Argyre Basin.
Cool.
So
Thank you.
that dovetails nicely with what you said. So
James Day, Scripps Institution of Oceanography. Those really nice talks. I really enjoyed them. Unfortunately, I'm going to pick on Alan because he's a rabble rouser. Thank you for sharing our data and showing it up again. That's really nice. One of the things I noticed you didn't do was show mesostasis versus the compositional variations, which is, of course, where most of the bulk rock rare earths are and incompatible trace elements.
Right.
But that's not really my point. My point is going to be the augite cores in all of these rocks, if they're not cumulates, should be the augite cores, if they're not cumulate, should all be distinct. The fact is that they're all very, very similar augite core compositions. I just wondered if you can comment on how that affects your model.
You're talking about like the major element compositions, the MG.
That's correct. Calcium, iron,
Yeah.
magnesium.
The thought I had on that is that you're absolutely correct that the major element compositions of the cores are all essentially the same, and also more compatible elements like vanadium and scandium are essentially the same across all of them. And my thought on that at the moment is that those are buffered by augite in the mantle where they form, so that what you're seeing is that the major element, the compatible element compositions are being buffered by whatever in the source region, whereas the incompatible element abundances are coming from somewhere else.
Okay, that will be a major test of your idea. Thank you.
Absolutely.
All right, before our next in-person question, we have one online question from Daniel Sheik, question for Sophie. Have you applied or do you plan to apply the vanadium oxybarometry technique to lunar samples, i.e. Mare basalts or eucrites, to test for consistency of this technique across different groups of planetary basalts?
That's a great question. So I know, Daniel, that you emailed me about this kind of already, but well, the whole reason I did these experiments is because you can't necessarily apply the same calibration of the vanadium scandium ratio to other planetary bodies. If we could, then there'd be no point in my experiments, and I would just use the terrestrial equations. But like, there is a difference in terms of composition, so I wouldn't say I could confidently apply this oxybarometer to, say, the augites in the knocklights. I would have to take a look at their bulk compositions, see how comparable that is, to be able to determine that. So while it'd be great if I could apply this to any planetary body, I think sadly, so many more experiments by hopefully other people are needed to constrain that.
Takashi Nikoichi, University of Tokyo. So I also have a question for Alan. So it's a nice data comparison. So if you have the NACRA and the Faggot only cumulates and the GRs does not, if so, do you have any good idea for the geological setting to explain?
Can you say that louder, please?
Geological setting for the to explain the two rocks are.
Oh, the geological setting for
Yeah.
these rocks. You know, I'm sort of in the same position.
Yeah, so it is
as Sierra here, that I'm not really sure that I can distinguish a flow from a shallow sill as far as its cooling. You know, some of the noclides have very, very fine grained, almost glassy mesostasis with really elongate oxide minerals. You can imagine those could easily be flows. Something like NOCLA and NWA 998 look very much like fine-grained plutonic rocks. So I guess I'd have to say that there's certainly a range of emplacement locations for them. Some are flows. There aren't any that have vesicles that I'm aware of. So maybe we're not looking at lava tops, but certainly there's a wide range of cooling rates that are represented, and therefore a wide range of emplacement locations.
So yeah, just I'm going to take chair's prerogative here and just ask Sierra, can you comment a bit on that, and also on, you know, whether the CSD results that you have it, you know, can be reconciled with what Alan's talking about, or, you know, what are your thoughts?
So this is on, right? It's so like I can't hear myself like I could with the life of one. So for our CSDs, that's really going to tell us more so about the kinematic state of the magma that the pyroxenes were crystallizing from. So for that, not necessarily to be able to distinguish the environments that they could have been placed or solidified in. The petrofabrics, we are primarily seeing foliations, which we associate with a flattening pattern in our magma. And if you remember from my last slide where I had that schematic, those types of fabrics can occur in any of those environments that I had up there. So they include the potentially shallow magma chambers, lava flows, shallow intrusions like sills or dikes, or as has been suggested from EBSD studies, potentially lava lakes or lava pond infills. So the actual settings and emplacement for the noclides are going to be pretty variable if we consider their textures, like Alan had mentioned, and it's not quite clear cut where we can say they might have come from yet. My paper is in the works.
Great, thank you. Next question here.
Please say for JPL. My question's for Sophie, just barely see. Really nice experiments. I have a sort of two-pronged question about the effects of pressure. So for the pyroxene cores, you know, the beauty of the vanadium-scandium ratio is that you see through crystallization processes. And so I wonder, the first question is whether your method can say anything about the mineralogy of the mantle sources. For example, whether or not the melting was in the spinel or garnet facies. And the second question is, did you consider the effect of pressure on the absolute FO2 of the FMQ buffer? Your experiments were at 1 atmosphere, but presumably the pyroxenes were crystallized at some depth. And so the FMQ buffer will change as a function of pressure. And I just wonder if you included that in your quantification of FO2.
Sure. So I'll start with your first question. I have not looked at how the vanadium-scandium ratio of these samples could tell us anything about the mantle sources. I think I would need to run a couple of models on like melts to be able to answer your question, but that's a great point for further research for myself. So I appreciate that. In terms of the pressure dependence of the FMQ buffer, it's not huge. Really, temperature affects the FO2 that you're looking at using QFM much more significantly than pressure, which is why I didn't do high pressure experiments. So there might be an effect, but based on the literature that's currently out there, it shouldn't be relatively significant. Thank you.
Good online questions. No additional. Okay, yeah, go ahead.
Hunter Edwards from Scripps Institution of Oceanography. I have a question for Amanda. So I was wondering, you demonstrated that the pyroxenes and olivines did not crystallize at the same time, which is pretty common amongst olivine ferric sugartites. Do you think that these do you think that the sample crystallized in a subsurface sill or perhaps in some sort of layered like lava flow where the olivine kind of settled out and the lithology B did not have any olivine in it?
Oh gosh. So there's several theories that are kind of debated about the origin of lithology A. You always have to account for the presence of lithology B. And the theories range from anywhere from a magma mixing environment into a shallow emplacement, maybe assimilation in a shallow setting. There's a theory that it's, the fine grained ground mass of lithology A is an impact melt that incorporated those mega crusts into the melt. And it was just in the presence of the lithology B. I don't think in the immediate sense that the zoning profiles alone are going to answer which one of those settings is relevant. But one thing I did notice is that the titanium zoning in my olivines, it abuts up against pyroxenes, and it doesn't appear to be depleted at the outermost rim. It seems to be pretty consistently enriched as it hits the edge of the grain. If it is in the presence of pyroxene, this titanium enrichment in olivine, as it's cooling in a magmatic setting, you would expect to see titanium leach out of the olivine, diffuse into the adjacent pyroxene, and I don't see that. So whatever happens to form lithology A, that olivine had to be in the presence of pyroxene for a very brief period of time as it cooled. And I don't know what the implication of that is yet. I'm hoping that the chronometry will help a little bit about whatever the time scale would be.
Thank you very much.
Thank you.
I'd just like to ask a question of Sojiro, if I may. Yes, over here. And so you showed some very interesting data from the microzanes, the iron and the mescalinite. I'm just wondering, for the enriched sugartites, you have larger error bars. Can you comment on why that is? Is that an instrumental variation, or do you think that's a real variation in ferric iron content in the mescalinite?
The uncertainty of the observation in the enriched shagotite is large than other shagotite groups. This is because I think the assimilation of the enriched material, because the enriched shagotite, the cooling rate of enriched shagotite is very fast. So I think the position of crystallization of enriched shagotite is near the edge of intrusive magma. So I think the low Fe content project crystallize in the later early stage in the crystallization, and high iron 3 plus project race is formed in the later stage after the assimilation of the enriched cluster material, I think.
Very interesting. Thank you. Francis?
So I've got, you hear me? I've got two questions. My first one's for Alan. So Alan, as you know, there are a lot of similarities between the chassignites and the noctilites, and they've been possibly proposed as being part of the same magmatic plumbing system. You refer to this sort of addition of a creep-like component. And looking at the chassignites, there was work by Wadwa and Prozaz showing that there is a change in the light rare earth element to heavy rare earth element profile in the cores versus rims of the pyroxenes, and some of the chassignites, and some of the work we've done since also sees an enrichment in chlorine that seems to be around the same time as this introduction of a light rare earth element component. And then that seems to be pervasive throughout the noctilites with this sort of chlorine enrichment and light rare earth element enriched component. Have you considered that in your model, and what the implications might be, particularly on the other end with when you're losing that chlorine enriched fluid, and how it would affect the melt composition?
Yeah. The fact is, no, I have not really considered that. I haven't even thought about chlorine and stuff in that, and I'd honestly forgotten about that difference in the cores of the augites from the Wadlow work. That was a while ago. But you're right that the Shawsignites and Knocklights are very closely tied in trace element chemistry, in age, and I've been asked about the trace element chemistry, and if there is some kind of metasomatic component in the mantle, some creepish thing or some autometasomatic material developed like around a plume, it's going to influence the mantle dunites as well as the mantle peroxenites. So at least that might be a way to start thinking about the trace element composition of the Shawsignites. The rest of your question, I have no good answers for. I haven't thought about that yet. Thank you.
Yeah, I would look at the Shawsignites for maybe what that creep like component is and when it came in.
That would be a really interesting thing to figure out. I mean, the thing about the Knocklights we have that as I saw them, there are none that do not show an influence of that. And it would be really interesting if maybe the Shawsignites had some component where we could see creepish addition to it.
I'd
That
be
would
happy
be
to
really
talk
cool.
with you more offline about that if you like.
Yeah.
And then my second question was for the last speaker on the noble gases. It's a fantastic data set, very impressive. Do you have a preferred explanation for why you have this mismatch of a chondritic, krypton composition in the mantle and the atmosphere being solar?
Oh man. So, I mean, anything I say ends up being hypothetical. So I think you again, like I said, you have to start off with Mars forming the majority of its interior, the majority of its mantle in the first few million years of the solar system. So you have all that chondritic material around to contribute. And like I mentioned that maybe there's like some solar cometary or planetesimal source that provided gases to provide the solar composition we see in the atmosphere. I'm not really aware of ones that are able to match the krypton compositions such that you would get that. So I think it's more likely that Mars is still even forming its present day atmosphere that then gets modified in that same 4 million years of the solar system after you've sort of built up the interior. That would be my best guess.
Well, thank you very much.
Thanks. Go ahead.
James Day, Scripps Institution Oceanography. This one is not for Alan. It's for the last speaker, actually. Again, I was really impressed with that data set. I do have a question, though, and it's probably one where you are going to groan. Are you going to measure xenon in your samples, or have you already done it?
Oh, I didn't mention it for convenience, but for all of the meteorites that we measured, we got neon, argon, krypton, and xenon measurements. So
do you have any insights into ionization loss of xenon from Mars's atmosphere and what these might tell you?
Yeah, so like I haven't looked at the ionization loss yet. We are like, because some of the it was literally just like a week ago we looked at some of the first xenon data to try to parse out when we see the solar effects. Is that coming from the atmosphere, which would probably have those losses as well as enrichment in 129 xenon, versus a more solar composition that would be more broadly homogeneous.
Perfect. Thank you.
Again, Takashi Mikoichi, University of Tokyo. I have a question about the vanadium oxybarometer. So once I also did the crystallization experiment using the QUE 94201 composition. And if my memory is correct, at high FO2 like QFM, for the liquidus phase, we had the spinel and then olivine. And after that, we had pyroxene. And at low FO2, like IW +1, so it's like a QFM -3. We didn't have olivine, we didn't have spinel, and the liquidus phase was pyroxene. And so my question is, did you have a similar result? And if that's the case, and expect that the distribution of vanadium should be different by the different liquidus phase. So
Sure. Well, some of the experiments crystallized olivine, some, well, olivine and pyroxene, some only pyroxene. You can check my abstracts if you want to know at which FO2 those were. I did not find any spinels in any of my experiments. I'm not sure why. It's possible I didn't go high enough in terms of temperature because my experiments were at either 1050 to 1100 degrees Celsius, which is why I'm gonna run higher temperature experiments to see if I can get some of that spinel because yeah, it's definitely gonna have an effect on the partitioning of all the different phases. But that's future work, so stay tuned. Maybe we can have a better discussion in the future.
Okay. Hi, I'm Brian Balta, LPI. I'm going to ask one of Amanda. Get her woken back up. Hi. Hi, Amanda. So you showed a phosphorus map on one of your olivines, and there was a similar map, I think of the same grain in your abstract that seemed like the contrast was different.
Yeah.
And the one in your abstract looked wild. I've never seen a pattern like that. It looked like the contrast had been reduced. So first, what technique did you use on mapping the phosphorus in olivine? Was that the standard high current microprobe technique? And second, if that's what that looks like, I've never seen one that looks like that. Do you have any interpretation on that one?
Yeah, I agree. So yeah, standard 500 nanoamps, a really long dwell time. So really cranking up that beam current, sitting on it forever. And yeah, I've never seen anything like that. It seems it has a very similar, so it has like these like veinlets that are running through. I think that it's just following microfractures. It might be some kind of like alteration. It does not look primary. It is similarly enriched in calcium in the same areas, but not quite to the same extent. I don't see anything that looks like primary zoning preserved by phosphorus at all. I don't see any primary zoning in that inner core at all in any element. And I do see a melt inclusion, and I do think it might have formed initially rapidly. I think that we're losing those primary signatures because it might have sat long enough to completely diffuse in terms of all of those elements. But I think that those crazy patterns, I think that those are microfractures through the olivine. It has a very complicated, it looks like it's been shocked pretty thoroughly multiple times, and I'm hoping the EBSD mapping will help a little bit to resolve some of that.
Thank you.
Yeah.
Okay, go ahead. We have time for another one.
Hi, this is Julie Zhang from Washington University in St. Louis, and I have a question for our last speaker. So Mars must have formed really early, and it is chondritic. I know that in our field we use ABCC, Q all the time, but if it's Mars, it's more NC than the Earth. So have you looked at inside chondrite krypton measurements, and do they show any difference from ABCC? And if they're very depleted in abundances, does that have any impact on your outgassing concentration versus like solar?
Yeah, that's a good question. I haven't looked into those yet. So for all of those krypton isotopic measurements, one thing I will mention is there's been some recent papers around zinc isotopes that show that Mars only has a very small contribution of carbonaceous chondrite material for its moderately volatile elements, and that most of it came from a non-carbonaceous reservoir. And so how one might interpret what I showed with the krypton isotopes is that you have maybe more of a, again, more non-carbonaceous contribution of krypton that would be more similar to the ansatite chondrites, but then maybe you mix in some of that solar krypton to bring the ratio down slightly.
Yeah, I just think that when you make the like more, if it's more depleted in krypton abundances, and then it will impact how much you need to maintain the solar, like present day atmosphere.
So we need to take we need to take any other comments on that offline. We're at the end of our session. Apologies for those who didn't get to ask their questions. Please do come talk to our speakers. Let's thank our speakers again. Thank you to AV folks as well. Big hand there. Thanks for keeping things running smoothly. And a reminder, there's a Martian Meteorites poster session tomorrow evening, so we'll see some of you there.